In this video, a demo of the MESON Industry 4 use case is presented. The discussed use case describes two warehouse robotic services and their interactions in a smart factory. The one undertakes the storage and the other the retrieval of loads from defined storage locations. These services are deployed and operated as different network slices composed of specific VNFs in a chain. Through the cross-slice communication link, the asset retrieval VNF can trigger the asset storage VNF when product availability is below threshold. Starting from the AR slice, the slices are deployed through the MESON platform, which is located in the University of Macedonia, as also the OSM. MTUA infrastructure is the edge pop, where an OpenStack is used as the virtual infrastructure manager. The corresponding application descriptors and the network slice templates are onboarded on the MESON agent and the OSM and contain essential information about the slice deployment, such as the location of the edge pop, the network service descriptor references, and the service KPIs. In the main screen, we can see the MESON agents and the OSM operation workflow, while in the nested window at the top right, we can see a view of the NTUA's OpenStack during the slice instantiation. For each slice, two virtual networks are created, one management network and one data network. MESON layer components are responsible for storing essential information for the cross-slice communication slices after a successful instantiation in the corresponding edge point of presence, which in our case is the NTUA's point of presence. Up next, the instantiation of the load asset storage slice takes place. The corresponding descriptor files are onboarded on the MESON agent and the OSM. As it's shown in the application descriptor file, the load slice requests cross-slice communication with the unload service in order to be operational. Besides that, cross-slice communication constraints such as preferred edge pop location and tenants requirements are defined. The corresponding descriptor files for the load slice are onboarded to the MESON layer. As this is a CSA request, MESON core components perform service matching and selection of the instantiation's edge infrastructure based on the descriptor input. These operations are quite fast, as they take about 50 milliseconds to finish. As previous, two virtual networks will be created, a management network and a data network. After the successful instantiation of the load slice, cross-slice communication establishment operations take place. These include the cross-slice communication network creation, the cross-slice communication VNF instantiation and configuration, and the establishment of a secure data network connectivity between the unload and the load slice. The entire cross-slice communication establishment workflows demands about 9 seconds to complete. In the next part of the video, a view of the corresponding APIs interactions through the cross-slice communications link is presented for those specific slices, the load and the unload. Unload slice is responsible for unloading the assets from the cells of Smart Factory. The whole operation is dictated by the mission planner VNF, which assigns missions to the robot to take specific amounts of assets from the inventory. Unload VNF undertakes the tasks of receiving the list of the required assets to retrieve from an external service, maintaining an updated view of the inventory database, and invoking the cross-slice communication mechanism in order to inform the load slice of potential asset shortages. In both slices, the localization service VNF constantly computes the precise position of the robot. Here, we assume 3 specific locations in the smart factory. The unloader VNF triggers the loader VNF when an item's availability is below a predefined threshold through the cross-slice communication mechanism. The load slice robot reloads out-of-stock assets at specific locations, and through the cross-slice communication link triggers the unload slice. The next videos highlight the effect of the cross-slice communication of mission completion time. We assume an operation floor that consists of 3 different locations, each located with a unique type of assets. We also assume that the mission of the unload slice agent is to collect a set of 2 different assets, one from each location. We also assume that assets can go out of stock, and it is the loader slice responsibility to reload them. In the first video, we have the collaborative case in which the 2 slices leverage the cross-slice communication capabilities of the infrastructure. The unload slice triggers the load slice when a shortage is detected after an asset retrieval, and only then the load agent is invoked to refill the respective location. In the second video, we have the independent case in which each slice operates autonomously on the factory floor as no communication takes place between them. And of course, in this case, the load robot periodically checks the asset stock in the three locations independently of the unload mission.